Welcome to Real Analysis. This is Math 131 at Harvey Mudd College. Real Analysis is an exciting subject. It is one of the first courses that a math major takes, and there's a good reason for it. Analysis, as I hope to show you, it involves more than just learning something about mathematics. It's also something about the process of doing mathematics. Okay, so in this course, we're going to be thinking a lot about real numbers, as the name implies, but we will be also talking a lot about the process of thinking of how to communicate mathematics well, write proofs well, and a host of other issues related to communication of mathematics. So let's begin. What is real analysis? What is real analysis? Let me start with a quote from Kronecker. Some of you may recognize the name. Kronecker was a mathematician responsible for the Kronecker delta, which some of you might have encountered in physics as a notation. Kronecker said in 1886, "God created the integers. All else is the work of man." What did he mean by that? Some thoughts. What did he mean by that? Feel free to give me your speculation. Yes?
The integers are really easy to grasp in a way, and like, as soon as you had everything in between stuff, it starts to get really sort of mucky.
Okay, the integers are easy to grasp. Tell me your name.
I'm Dylan.
Dylan. Thank you, Dylan. Mary.
Well, even animals can understand small integers. A bird can tell the difference between 2 and 3, but they don't have a grasp of other mathematics. Those are things that are created by humans, things that we've come up with.
Okay.
There's sort of an innate understanding in nature of integers.
Okay, so Mary's response was that even animals can do integers, but maybe there's something more that we as humans can grasp. Katie.
Integers occur in the natural world. So you have 3 chairs, 6 people, and I mean that's something that it just occurs. But calculus just doesn't occur in the natural world. You have to discover it and create it.
Integers occur in the natural world. Calculus doesn't just occur in the natural world. What do you mean by that? Because some might say that it does.
Calculus describes the natural world, but you don't see an integral just lying around there.
Okay. You don't just see an integral lying around. Interesting. Other thoughts? What do you think Kronecker could have meant? God created integers. All else is the work of man. Yes?
Integers are the basis for a lot of math, but things like the rational numbers are constructed by people through combinations of integers, stuff like that. You can build a lot of math using just the integers.
Okay, so mathematics is built up from the integers through some construction process, and we're in fact going to begin to talk about what that means in a second. Other thoughts as to what Kronecker could have meant? Any other thoughts? All else is the work of man. Do you think he was being somehow somehow derogatory of what man can do? What do you think? Yes, Paul?
You mentioned he showed up in physics. He might have been alluding to the fact that things are a little more discrete, although I don't know if he knew that at the time.
Okay.
But that nature is more discrete and that continuous mathematics are nice and all, but don't explicitly show up in nature.
Okay, so Paul is suggesting that perhaps Kronecker was happier with discrete things than continuous things, which one might argue don't really show up in nature. Interesting. Okay, well, let me tell you a little bit about the genesis of this statement. So Kronecker had a very unusual point of view, mathematics, at least it was unusual at the time, and it is in fact unusual today. And that is, these are the questions that I was going to ask. Do you agree or disagree? Kronecker had an unusual point of view. He was what you might call a finitist. Okay, so this is a point of view that mathematics should only deal with finite objects, finite numbers, or things that could be constructed from the numbers in a finite number of steps. Okay, so in some sense here, when you hear what he's saying, somehow the integers are special. They're God-given in some sense, right? And everything else, well, it's just the work of man. And so the consequence of this belief is that, for instance, Kronecker was opposed to the use of irrational numbers and doubted the significance of non-constructive existence proofs. Okay? And so some things that we take for granted today, which would include the length square root of 2, is something, the existence of the use of the square root of 2 would be something that Kronecker would have a real problem with. Okay? And this particular quote was in fact a response to Lindeman's proof, recent proof. It was 1882 that he proved that pi was transcendental, which in fact means that it's not the root of a algebraic, the root of a polynomial with integer coefficients. And his response, Kronecker's response was, yeah, that's beautiful. It's a beautiful proof, but it's of no importance because, as we all know, transcendental numbers don't exist. And in fact, Kronecker's point of view met with a lot of resistance because people felt slighted often by his comments, which to them seemed like he was dismissing a whole areas of inquiry which he shouldn't be dismissing. So I think the message that I want to begin this course with is that there's a lot of things that we take for granted that weren't always so obvious. I mean, you might come to a course like real analysis, which some of you know. We do a lot of things. We derive calculus from its foundations in some sense. And you might approach this course with a point of view where you say, gosh, you know, isn't everything we do in this course kind of obvious? Well, it's not, and I hope to convince you that there are a lot of things which to us appear obvious because we learn things a certain way. So if you think back to the Greeks, you know, they understood something about rational lengths. I mean, they were interested in constructible lengths, constructible numbers. Okay, they were interested in what you could get by using a ruler, a straight edge, and a compass alone. Okay, and so they knew how to construct rational lengths. You know, if you asked for a line of length 4/5, they could show you how to do that, given a line of length 1. They also knew there were other lengths on the line that were not that were constructible, but not rational. Okay, and so this, of course, involves you can show that the square root of 2 is not a rational number, which we will do in this course. But it is constructible because, after all, you can, if you've done anything with a straight edge and compass, how many people have worked with a straight edge and compass at some point? Okay, yeah, you can construct two lines that are orthogonal, that are perpendicular, and you know, measure off a length here and a length here, and then this one is the square root of 2 times that length. It's a constructible number. The Greeks knew about other lengths, like pi, but they couldn't find a construction that would give a line of length pi. Okay, and so there's a big question was whether you could construct the length pi using straight edge and compass. So it turns out that you can't construct pi, and that's because it's transcendental, and constructible numbers are always algebraic and therefore not transcendental. So we know that it's not possible now. But pi can be obtained, as Newton showed, and Wallis. It can be constructed through infinite process, and Newton came up with an infinite series that you could sum that would yield pi. But what is an infinite series? So this begins to beg a question. Okay, so already here, 200 years before Kronecker, Newton and Leibniz, in developing the calculus, began to encounter the infinite. Okay, and they didn't have a real rigorous way of dealing with the infinite. In fact, if you look at a lot of the history of calculus, it was a toolbox at first. Okay, it gave good answers, but there was not a precise notion of what it meant for a series of numbers to converge. Okay, there wasn't a precise notion of limit. And if you have a series of numbers, an infinite sum, that is in some sense a limit of a bunch of finite sums, right? But what does it mean for a set of numbers to converge? Are there even enough numbers available to capture all the limits, right? If you only have natural numbers and rational numbers, yes, they can be ordered on a line, but why is it the case that if you start putting in, let's say, first all the rationals, first all the integers, and then all the rationals, okay, don't make me do them all. How do we know that what does it mean for these things to fill out a line? And they don't, of course, because we know that there are other lengths in here. But once you start talking about sequences of numbers converging, is it possible maybe that a sequence of numbers converges in some sense, but doesn't have a limit? There isn't a number there, whatever that means? Is that possible? What does it even mean for a sequence of numbers to converge when you're not referencing a limit? There's a question. Some really tough questions. And so even though the calculus was developed in the 1600s, it really wasn't until the 1800s that people began to worry about the foundations of calculus. Okay, so in particular, Fourier series are series that you might learn about in a PDE's course or something. They are infinite sums of sines and cosines. Okay, and they did rather strange things that made the mathematicians of the day very, very uneasy. In fact, some of them outrightly rejected Fourier's work. But nobody could deny that Fourier's methods actually gave answers, right? Where physicists wanted answers, it gave answers, and it seemed to give right answers. Why was that? So really, Fourier series wrestling with series and sums, infinite sums, brought about a revolution in the 1800s in making these concepts precise. And it was a lot of the work we're going to talk about in this course is work of Cauchy that has been certainly simplified and streamlined for your digestion, but was not necessarily so clear at the time. Weierstrass and Riemann, 1850s, 1860s, also were big players in this development. Many other mathematicians I could mention. But I just hope to give you a sense that many of the things we take for granted really weren't so obvious at the time, and a lot of it came out of wrestling with the infinite. So one of the first things we want to do in this course is actually show you how to construct the real numbers. Okay? What does it mean to construct the real numbers? So that is actually going to happen in lectures 2 and 3. But just to start off with something that you are familiar with, and to give you some sense of what it means to construct an object, we're going to start in this lecture by constructing the rational numbers. Okay? So that's our plan. Let's begin. And I'll use the board from here on out. Okay. So let's begin with some easy concepts, and just to make sure we're all on the same page, we'll establish some notation. So let's first talk about sets and relations. And I'm sure many of these concepts are going to be extremely familiar to you, but we're going to make sure that we know how to use some of these ideas carefully. So what is a set? Anybody? What is a set? A collection of things. And as easy as that sounds, the notion of set is something that mathematicians had to wrestle with very carefully in the 1900s. But we're going to call it a collection of objects. Okay. And there's a reason we don't say a set is a set of objects. There's a good reason for that. here's how we're going to write a set. So a collection of objects might be labeled with a letter. And I might notate what's in this set by putting some things in brackets. Okay? So for instance, a set could be a set containing, a number like the number 1, right? But it could also contain other objects, right? It could contain, a smiley face. That might be an object of this set, right? Could be a parallelogon. Parallelogon, yes, okay. It could even be, if you want, another set containing a couple of objects. Okay? A set might contain other sets. Okay? Oh, really? Interesting. So, just a little quiz here. How many objects does this set have in it? 4. Good. 4 objects. Don't be fooled here because this creature is one set. As a set, it is an object in this collection, which is another set. Okay? Everybody with me? Okay, good. Now, one of the things that you should begin to do when you are learning to write mathematics carefully is to make sure that what you write is actually a complete sentence. Okay? So, of course, when I do work on the board, sometimes there will be shorthand, but you should avoid that when you're writing mathematics carefully. And I will try throughout this course to write sentences. Okay, so a set is a collection of objects. Is that a sentence? Well, yeah, it is a sentence, but I haven't completed it. Okay, with a period. Okay, I want you to think about mathematics as communicating mathematics well as communicating in sentences. If you open up your textbooks, any textbook, you will notice this, that mathematics is actually written in sentences. So even equations. So here I'd write, okay, so this is a command, right? I'm telling you to write S like this, but I should complete this thought with what? A period. Okay, even displayed equations you'll see written this way in your textbooks. Okay, okay, very good. Here's another way we might describe a set. I might describe a set by telling you some property that it satisfies. So I might say, let S be the set of all little x. And I write a colon here, which means such that little x such that P of little x is true, where P is a sum statement about x. Okay, so what do I mean by that? An example would be something like, let's look at the set of all x such that x is less than 2. That would describe a property about x, and if it's true, I will put it in this set. Everybody with me? And what should I do? How about a little period there? Okay, I'm completing the thought. Okay? Okay, so in fact, let me just do this. I'll say e.g. x is less than 2. Period. All right. Now, there's lots of shorthand, which will be helpful to us, so I don't have to say, to write down a lot of things. So I can write some shorthand when it's convenient. So we'll often use this notation. X, let's first do in. X is in S, so this means X is in S. Period. And there's the other notation with a cross, which means X is not in S. Okay. And every once in a while I'll put these little quotes, which means repeat what's above. Okay. There's a special set, which we often want to describe, and that's the set with nothing in it, otherwise known as the empty set. Very good. And it has a special notation, which is basically a circle with a slash through it, is the empty set. Okay, very good. Here's another notation, a shorthand we'll want to use. So if I write, there's sometimes I want to say that one collection of things contains another collection of things. One set contains another set. So if I write A with a sideways symbol like this, it means A is a subset of B. And I have to now tell you what it means to be a subset. What does it mean to be a subset? Or you could say it another way. What this means is, okay, so it means this. So I'll say which means. What does it mean? Well, it means if. So how would you describe this definition, A is a subset of B, just in terms of a relation involving set, what's in a set or not in a set? Willie?
So for X is in B for all X in A.
Okay. Yeah, so another way I'll write this is if X is in A, then X is in B. So it means this whole statement. If X is in A, then X is in B. Okay? Another way we can write this, I'm just giving you lots of ways of saying the same thing. You could notate this by saying one implies the other. So you'll see this implication arrow. This should be familiar to most everybody with the prereqs for this course, but just being careful here. One thing you do also have to be to watch out for is that with this notation, some authors, well, generally this also includes the possibility that A and B are the same set. Okay, but some authors emphasize that by placing an equals underneath. But if you don't see, you should assume it could mean that one is contained in the other. So here's another thing. If A is in B and B is not in A, that is, one is a subset of the other, but not vice versa, then we call A a proper subset of B. Okay, so it's strictly smaller. And if A is in B and B is in A, then we will write A equals B. So this is what you'll check if you want to show two sets are equal. One strategy is to show that one is contained in the other and the other is contained in the first. And if A is not equal to B, then we'll write A with a not equal sign B. Okay? Okay. Just being careful about some notation here. Okay, so let's establish a little more notation, and then we'll begin to talk about relations. So you can construct new sets from old. So more sets. If you give me a couple of sets, there's some operations here I can do. So for instance, I can talk about the union of A and B. So the union is A union B, right, a little cup between the A and the B. And what is the union of A and B? Somebody describe that to me in words. Somebody describe that to me in words. Rebecca.
All the elements of the set A and all the elements of the set B.
Okay, so if I were to write it instead of as the first way, instead of listing the elements, which I obviously can't do, if I write in terms of a property, what should I do? How about the set of all x, little x, such that, what did you say, Rebecca? Good. X and A or is it and? Good. Or X is in B. Okay. Okay. And here's an associated notion, the intersection, which is written with a upside down cup in between A and B. And it's the same definition except what? Or becomes and. Okay. Okay, good. Here's another one, a complement. There are many notations for this, but we'll use a little c. The complement of A is defined to be the set of all x such that, help me, x is not an A. Okay, very good. There's the minus operation, which is written with it's not quite a minus symbol. It's kind of a slanted minus symbol, a backslash, and that's to remind you that these are sets. So take a guess as to what this notation might mean. Good. X such that X is in one but not the other. In particular, you want to say X is in B. And X is not an A. X is in B. Oh yes, sorry, my notes are backwards. I had B minus A here. So X is in A, but X is not in B. Thank you. Very good. Okay, and then this one is going to be important, especially important in what follows, and this is the product of two sets. Involves a new idea, and that is you can collect elements of sets together. So the product here is going to be a pair, little a, little b, such that little a is in big A, and not little b is in big B. Okay. Now, this is a new idea. This is an ordered pair. It's not a set, per se. It is an ordered pair where order matters, because you want to indicate the first thing is in A and the second thing is in B. Okay? Product. Excellent. So now we want to come to the notion of a relation. What is a relation? When I say the word relation, what do you think of? What do you think of? Malus, when I say the word relation, what do you think of? Good. How do things interact with one another? Okay. So, for instance, I might say that Malus is the sister of Paul, which may or may not be a true statement. Okay, that's a relation, right? Or John is the father of Mary. That is a relation. Okay, so these are relations that involve two objects, and so we'll refer to it as a binary relation. Although if you talk about a relation without saying what it is, you often mean binary. So we might give the relation a name. We'll call it R. And here's a new way to describe a relation. It's probably going to be new for some of you. We'll describe it as a subset of another object. Let's say a subset of A cross B, the subset of a product, such that something is true. Well, actually, no, sorry. It is a subset. There'll be some relations that determine what actually lives in the subset. But we normally write this as follows. So if A and B are in R, we often write it like this. We'll write A, R, B. This is a statement that basically says the pair AB are in this subset. So let me give you an example. The relations that you are very familiar with. So I might have the relation A is an ancestor of. So this is the relation is an ancestor of. It's a relation on what set? Well, it's the relation on, well, I usually compare two people when I talk about ancestors. So this is the product of the set of people. Okay? With me? L, the relation to like somebody, is also a relation on P cross P. It's a different one, right? Because you might not like your mother. Okay? But if you look at the set of all people, and you look at ordered pairs of people, I might ask, is the pair Bonnie and Jenny in the relation A? Does Bonnie A Jenny? No. But does Bonnie L Jenny? We hope so. That's the right answer in this audience, right? Okay. Okay. Here's another example. S is a sibling of. Is a relation also on people cross people. Actually, you know, the like relation doesn't have to be just a relation on P cross P. It could be a relation on P cross a whole set of objects, right? T, another set. Okay? Okay, here's a relation that you're very familiar with. It's a symbol. It looks like an arrow, a caret pointing one way. It usually means what? Less than. This is a relation on, usually, if you like, since we haven't talked about real numbers, we'll just stick to integers, which are denoted by the letter Z. And so you're used to seeing this symbol used to say 7 is less than 10. That's a statement where the relation symbol lies between the two objects in the binary relation. Are you with me? Okay. That's all it means. But the way I want you to think about this is it's actually just a subset. I have described what a relation is completely in terms of something very basic, membership in a set. Are you with me? Okay, that's somehow comforting. All right. Good. So we have some examples of relations. One of the most important examples of a relation is, in fact, something that you might have encountered in another course, and that's the concept of an equivalence relation. So the equivalence relation on a set S is, well, it's a relation on S cross S, whatever that is, such that, and I'm going to start abbreviating such that by ST. Such that three things hold. Let's give this relation a name. Let me call it R. So what does it mean to be an equivalence relation? Well, we want a word that somehow describes relations that of things being equivalent to other things. Okay? So for instance, equals is a natural equivalence relation, but there might be other kinds of equivalence relations, right? Another equivalence relation might be something like, okay, all the sophomores in at the colleges are somehow equivalent, right? Okay, so if we want to make that notion precise, well, maybe they're not equivalent. You're debating that. What do you want to be true about an equivalence relation? Yes.
You want if the product A B is in R, then
Okay, so you're saying if A are B, then B are A. Okay, that's good. That is one of the things on our list. It's not the simplest thing on our list, but it is one. So we want it to be the case that if A are B, this implies B are A. That is, if the relation goes one way, then it goes the other. And we have a name for this. What do you think we call it? It's the symmetry relation. Okay. There's a simpler one that you might demand to start. Yes. Remind me your name, too. Laura.
Things should be equivalent to themselves.
Good. Very good. So ARA better be true. Okay. And there's a name for this. Anybody know what it is? It's the reflexive condition. Okay. So good. Let's look at some of these relationships. Is A reflexive? No. I'm not an ancestor of myself. Okay. Is L reflexive? I hope so. I hope so. Okay, good. So is L symmetric? If Bonnie likes Jenny, does that mean Jenny likes Bonnie? Not necessarily, right? Okay, very good. And there's a third relationship that you might hope to be true as well for an equivalence. You want to say a bunch of objects are equal, and I know this is in, these two things are in the relation, these two things are in the relation. What's a third thing you might hope to be true? Katie?
If A are B and B are C, then A are B.
Okay, good. If A is related to B and B is related to C, then A better be related to C. This is called transitivity, okay, the transitive property. Okay, so these are the three things that you hope to be true, and I'll put a period here and commas just to emphasize the sentence is complete. Okay, and you often write something like this. The equivalence relations are often denoted by something that looks like an equal sign, right? It might be tilde, or it might be double tilde, or sometimes tilde with an equals. There's a lot of ways to write equivalences. Okay, you generally avoid using the equal sign because it's reserved for actual identity. Okay. Okay, good. So that's an important example of an equivalence of a relation. And I'll just mention one other important example, although this is the one we'll want to deal with today. As an aside, here's another important example of a relation. So I claim a function is also a relation. So a function from, let's say, A to B is a relation. So, okay, now, of course, when you think of a function, you think of maybe something like the letter F, right? And you think of what? Well, you think of F. You often write F colon A arrow B, right? What's true about a function? What makes a function a function? Yes, Jenny.
If you're going to think of it as a relation that where every element in A, there's only one pair, AB, which is part of it.
Very good. So each input gets sent to one and only to one out to unique inputs have unique outputs, right? So one way to think about it is if I apply a function to a particular element here, let's say I put in a person and I get out their bank account, the money in their bank account. Then you'd hope that every time you enter the person, what you get out is still the same number, okay? Which is not necessarily true about bank accounts over time, right? If you want to turn that into a function, you probably want to add another input, which is the time, right? Okay, but the idea is there is a it's a rule that assigns to every element here a unique element here. Let me just convince you that this is also a relation. Right? So it's a relation such that, I'm just going to write it down the way Jenny wrote it, said it, and that is if A, F, B and A, F, B prime, then what do you hope to be true? What should be true if it's going to be a function? Then B equals B prime. It has a unique output. So this is a rule. This is how we capture very formally the idea that it's a rule that assigns to each A in little a in big A unique B, little b, in B. Okay? Now, of course, we never write functions this way. We usually write functions this way. F of A equals B. Okay? But that's just a notation that describes this relation. All right. Very good. Everybody with me? Excellent. So we're going to take a 1-minute break, 2-minute break, stretch break. And after the break, we're going to construct the rational numbers. Okay? And I'm Okay, welcome back from the break. We are in the process of constructing the rational numbers as a route to constructing the reals, but also I want to show you what are some of the issues involved in construction of objects. So for instance, here, we're going to begin by using the integers. So this notation here, Q, means the rational numbers. And there's some things I'm going to assume, and one of the things I'm going to assume is that we know everything you want to know about the integers. So Z here, these are the integers. These include the positive and negative integers, whole numbers and the negative whole numbers. Okay? We're going to assume not only that we have the integers, but that they have, we know about their arithmetic, we know that we can add them and subtract them and multiply them, and we know about their order. Okay? Okay, so in other words, I don't want to go too far back. Okay? I want to assume that you guys know these things. Okay? Okay, so when we say the word construction, this often implies that there's some goal. Okay? What's the goal of this construction? What is Q? What do we think of when we think of the rational numbers? Just throw out some thoughts here. I mean, these are things you've learned since grade school, rational numbers. What do we think of when we think of rational numbers? Let me hear from someone you haven't heard from before. Tell me your name.
David.
David.
Have a finite number of decimal places.
Okay, that's one thing you think of when you think of rationals. And a terminating decimal has a terminating decimal expansion. What's another thing you think of? Name, please. Steve? Keith, okay. Can be written as A over B. Oh, interesting. Okay. Interesting. So, what is Q? There's a question. And a first answer, as Keith suggested, is maybe you write it like this, perhaps. So perhaps, here, let me write this as a thought. Perhaps it's a certain set. What set? Can be written as A over B. And in fact, let me do this in using different letters here, more traditional. M over N such that what's true about m and n? Okay, m and n integers, right? Because it wouldn't be a fraction if I put pi and pi over e here, right? Okay. Okay, very good. What else do you normally do with these with this notation? Not only demand they be integers, but I claim you demand something else about one of them. Yes?
Relatively prime.
Ooh, interesting. That's not something I'm going to demand right away. But what's a more important consideration? Second row here.
N cannot equal 0.
Good. Tell me your name. N cannot equal 0, David said. So m and n are in Z, and n is not 0. Okay? This is one possible answer you might give to this question, but it's not very satisfactory for a few reasons. But probably the most important reason is we have no idea what this notation means. What do you mean by m over n? Right? What does that mean? The integers don't have a division defined on them. Right? What does it mean? Okay, so I'm just going to say this is not quite good enough. Because we don't know what we mean by what with this symbol. What's this mean? Okay, so let's try to be a little more careful, and we can be guided by what we do know. So let's think about the motivation. So when we think about fractions, we're usually thinking about trying to teach children something about dividing, I don't know, cakes into pieces or something like that, right? So, you might, for instance, take a cake, which looks remarkably like an interval, and dividing it into, I don't know, 3 pieces, and giving somebody one of those 3 pieces. Okay? And we have a name for this fraction. We call it 1/3, right? Okay. 1/3, which really means 1 part of 3, right? That's one way to think about it. But there are other ways that would describe the same quantity, right? I could have divided the cake into 6 pieces and picked 2 of those pieces, right? So the 1/3, we normally write 1/3. And this, in this thing, we might say 2 parts of 6. And we could write 2/6. And we see already another issue, which is what? We have 2 different fractions, but they represent the same thing, right? Sorry, my microphone it really is falling. Okay, so this brings us to a concept here, which is, okay, well, we have 2 ways of representing the same thing. 2 ways of representing the same thing. These 2 things are, in some sense, we want them to be equivalent. Equivalent, okay? So maybe we want to set up a construction that's where we define fractions in terms of equivalence relations. Okay? How are we going to do that? What will the equivalence relation be? So how about this? Let's take any construction like any picture like this, and if I want the associated fraction, I will think of 1/3 as an ordered pair. So maybe I'll do the following. In the first picture, I'm picking 1 part out of 3. And in the second picture, I'm picking 2 parts out of 6. And I will think of these as equivalent ordered pairs. Okay, and to make this a sentence, I might say write that as equivalent ordered pairs, period. All right? Okay. And then what I will do, if I can, is once I figure out what all the things that are in that are equivalent are, The idea is that these belong to some equivalence class that might have lots of other things in it, right? Like 10, 30, right? Or 121, why did I torture myself? 363. Yes. Okay. These belong to some equivalence class, and we'll give that a name. We'll call that equivalence class 1/3. Are you with me? Okay. Now, once you have that, then of course you can just talk about fractions, right? And then everybody knows how to work with fractions, which are really disguised ways of dealing with the equivalence relation that's embedded here. What's the equivalence relation that everybody learns in grade school? When are two fractions equivalent? I'll have you think about that, but the set of all such classes will be called Q, which is basically the set of all such equivalence classes of pairs, of these ordered pairs. Right? What ordered pairs? The ordered pairs in Z cross Z. Okay. We might have to be a little careful here. Maybe Z cross Z minus 0. The set containing 0. Period. Okay. Okay, everybody with me? What have we just done? I've just defined what I mean by Q, right? It's an ordered pair, and its equivalence classes of ordered pairs. Now, what we haven't said yet is what the equivalence relation is. So, what is the equivalence relation? By the way, before we even talk about what the equivalence relation is, what's another thing you might want to be true about Q, aside from the fact that, I've just said that there's a set here, but somehow, how is it related to the set I began with? I might want to delineate that, right? I might want to tell you, how is it that Q is related to Z? And usually, the way you think about Q is that it somehow extends Z, right? You have a bunch of points. These are whole numbers on the number line that you grew up thinking about. And now we've filled them in with a bunch of other points in between, right? But are the points on the number line still there? Yes, they're embedded in Q, right? So you might want to say how Z is embedded in Q. Okay. So we want these pairs to extend Z so that, which classes will correspond to Z, to the elements of the natural numbers? What will if you give me the number 5, what class would you hope that it's somehow associated with? Yeah, how about 5 over 1? So that, for instance, n over 1 in Q corresponds to n in Z. Right, so this is the other thing we might hope for in our construction. Okay? Okay. Now, if you've taken an algebra course, then what you're looking for is an isomorphism of Z into Q. But if you don't know those words yet, that's okay. Okay, so tell me what the equivalence relation should be. So after grade school, or after enough examples, we see that what? Q is the set of all, let's say, m over n. These are equivalence classes, such that m, n are in Z. N is not 0, where m over n is an equivalence class of is the equivalence class of m comma n with the relation, what relation? Okay, tell me when p, two ordered pairs are equivalent. When will p comma q be equivalent to m comma n? Steve? Good. This is otherwise known as the, well, there's some name. You cross multiply to check whether fractions are the same. Yes, that's the equivalence relation. So with this relation, these are equivalent if what conditions are true. Steve suggested doing what? Let's take p times n and check whether it's the same as what? Q times m. And what else? Let's just demand that n and q not be 0. Okay. So if these things are true, then we'll say these two pairs are equivalent. Okay. Okay. Now, that's a relation. Is it an equivalence relation? There's some things to check here, right? We won't do them all, but I do want you to think then that, so here's the important thing to do. Once you have the construction, the work is not done. You should check that it's an equivalence relation. Check tilde is an equivalence relation. So, for instance, is it reflexive? Some of you said yes right away, and some of you hesitated. How would I check if it's reflexive? What would I have to check the reflexive condition for this relation, which is on pairs of pairs, right? You give me a pair and another pair. How would I check? What would I have to check for reflexivity? What do I want to check? What's the condition I want to check? What corresponds to ARA over there? Yeah, is PQ equivalent to PQ? Now, does everybody agree this is what we have to check? Not the only thing, but it's one of the things, yeah? Okay, good. Now, is this easy to check? Well, then you go back to this definition. This is why definitions are so important in mathematics, because we know what we mean when we have a definition. What does it mean to check PQ tilde PQ? It means checking that PQ equals QP. Is that true? For integers. Yes. Okay, good. So I'm not going to write it out, but you can write this out. Okay? I'm going to put ... there, which means you finish the argument. Okay? The other thing, of course, to check is Q and Q are not 0. Are they not 0? Well, by the ordered pair, but the set we defined, it's not. So don't have to worry. Okay, great. What's the second thing you might check? Symmetry. Okay, is P comma, okay, what does that mean? If PQ tilde MN, does that imply MN tilde PQ? First of all, do you agree this is what we have to show? Good. Secondly, can you see how you'd write this out, which I won't bore you with? This condition means Pn equals Qm, and this condition means this equals this. MQ equals NP. Is that the same thing? Yes, Adam says it's the same thing. So, again, I'll let you finish that argument. Now, the third one is perhaps the most interesting one, the third thing to check. Because if you look at it, it's actually not so obvious. Oh, I realized I could have used that board, but that's okay. Okay, this one says if PQ tilde MN, I got to check that this and if MN tilde, give me another pair of letters, maybe AB, then is it true that PQ tilde AB? There's a question. Is that true? Okay, so this is actually where it's very important to just be a little careful. Okay, so I'm going to give you a hint as to how this goes, and you can verify this. Okay, for a little bit of homework for next time. So one thing that you'll have to use. So try this. But you'll have to use a property of the integers, which is the cancellation law. You don't have division, but it's the next best thing to division. Okay? So the cancellation law in Z says the following. It says that if AB equals AC and A is not 0, then what's true? B equals C. Right, and the way, of course, to see that is basically because Z doesn't have any 0 divisors, AB minus AC can be factored. So it's A times B minus C equals 0. If A is not 0, then B minus C is. Okay, but use this fact. You'll be able to take these two statements and turn it into this statement. Okay, and I encourage you to try that in the privacy of your own home. Okay. Okay, great. So we've constructed Q, and we haven't, but I'll say something about this next time, we haven't yet talked about arithmetic on Q, but we will have to check a few things there as well. Okay? Great. We'll see you next time.